Hi, you guys. Welcome to your lesson about HR diagrams. So in this video, we're going to talk about the key features of the Hertzsprung-Russell diagram. This chart was first created about 100 years ago by two astronomers called Hertzsprung and Russell. Go figure. Okay, so when you look at the HR diagram, I want you to pay close attention to the axis. They might look a little bit different than what you've seen before. Okay, so first, the y-axis is the logarithmic scale of luminosity, which means how bright a star is, where the power or the output of our sun, or how bright it is, was used as the base example. Okay, Hertzsprung and Russell used how bright our sun shines to compare all the other stars that they could find against our sun. Okay, so in terms of the HR diagram, our sun is very normal. Everything was used to compare to it. It's the base example, okay? In order to do this, Hertzsprung and Russell defined our sun's luminosity, or L, equals 1. And then they used the scale and they rated all the other stars accordingly based on if it was brighter than our sun or dimmer than our sun. Was it larger than our sun or smaller? And you can see this example on the screen here, where the big circles are big stars, small circles are small stars. And then you can see on the x-axis that they recorded the star's temperature, either hotter or colder. And then they made the chart accordingly. So the scale that they rate other stars increases So the scale that they use to rate other stars increases logarithmically, with the most powerful stars being at the top of the diagram. Okay, so that would be up over here. And then the least powerful stars, meaning they're not quite as bright, towards the bottom of the HR diagram. Okay. Now remember I said pay close attention to the axis. That's because the x-axis is a little bit different than what you're used to seeing on a normal graph. The x-axis here describes the temperature of the star. However, it's reversed from what you normally see. The hottest stars are not towards the right. In fact, they're towards the left. Okay, so again, it's reversed from what you normally see. The hottest stars are about 40,000 degrees Kelvin, and they're on the left-hand side of this axis, okay? Then it gets cooler as we go towards the right, okay? And I understand that when you think of blue, you think cold, and you think red, you think hot. But in terms of stars, we're reversing those colors as well, okay? So streaking across the middle here is what we call the main sequence, okay? Most stars in existence are in the main sequence. Our sun is in this group by definition of the HR diagram. Remember, the creators of the HR diagram charted all stars in comparison to our sun. So our sun would naturally sort of fall in the middle here of the main sequence. It's actually right around here. Okay. All other stars in the main sequence are stable, and they're undergoing nuclear fusion to turn hydrogen into helium. These are middle-aged stars. Now, in the main sequence, there's a correlation between the star's mass, or how big it is, and its luminosity, or how bright it is. We can see this here on this example. So you see that how bright it is are the bigger stars, but then the mass of the stars gets smaller as these stars cool, okay? This is strictly for the main sequence. That's important to remember. In the main sequence, typically if you have a higher mass, you'll have more brightness. Okay, now I say this is only the rule for the main sequence because not other types of stars are this way. For example, towards the upper right hand part of the diagram here, we've got red giants. Now remember from the last lesson, red giants form from average size stars that used to be in the main sequence. After their time in the main sequence, they will burn the hydrogen in their core, and their core has been exhausted. And once it becomes exhausted, it becomes cooler. Okay, so that is why you see them here on the right-hand side of the diagram. They're cooler, okay? So they kind of come down towards the cooler side, but then they're going to have a higher luminosity than many of them in the main sequence because they're just so much larger. Okay, now when a red giant exhausts its fuel and burns everything off, it sheds its outer layer and leaves behind a very hot core. And that way it'll come back down and be in this kind of quadrant here, known as a white dwarf. Okay, it'll make this arch as it goes around the diagram. And everything at that point, everything is burning up. And as it burns, it's getting hotter and hotter and hotter. So we're going to go this way, hotter, 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 until it becomes quite dim and winds up in the white dwarf category. So the white dwarfs appear in the bottom left-hand quadrant of the Hertzsprung-Russell diagram because even though they're still very, very hot, they have a high temperature. Look at their temperature over here in this quadrant. They are not quite as bright because they're much smaller. They have a lower luminosity, okay? So red giants follow this path, but now super red giants are formed from stars that were in the main sequence, but they were super huge to begin with, okay? So they form from big, big stars. And instead of becoming a red giant, they become a super red giant. Now, to give you an idea of the size of a super red giant, their radius, remember that's half of a circle, can be up to 1,000 times greater than our sun. So that should give you an idea of just how extreme we're talking about when we talk about the mass of a super red giant, okay? These are huge, huge stars. Red supergiants are formed from very large main sequence stars, meaning not our sun. Our sun will never become a red supergiant, okay? Our sun is a medium-sized star, and it will graduate eventually, many, 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 many years from now, to be a red giant status.